All right. This section deals a lot with proofs. So it's called the mean value theorem. However, there is the mean value theorem and Rolle's theorem. And we're actually going to talk about Rolle's theorem first. Rolle', Rolle's theorem. Now, notice both of these are called a theorem, which means whenever I am coming up with a theorem that we're looking at, these are proof-based. So basically, you're going to have to work with proofs of this Rolle's theorem and mean value theorem, meet the criteria, and then make the proof. So that's kind of what this section's about, all right? It's a couple of proofs. It's not too bad. All right, let's look at Rolle's theorem. Whoops, that's not helpful. We're going to let f be continuous on a closed interval. And that closed interval we're going to say is from A to B, and differentiable on that same interval. Except whenever I say it's differentiable, it's on the open interval here from A to B, with f of A equal to f of B, all right? If that is happening, there is at least one point C in this interval such that the derivative at C equals 0. All right? All right, check this out. So there are 3 criteria that have to be met here. All right? Let f be continuous. Bam, there's criteria number 1. So 3 criteria have to be met before we can go forward. Criteria number 1, it has to be continuous on the closed interval. Criteria number 2, it has to be differentiable. And criteria number 3, f of A has to equal f of B. So the beginning function, the value at the beginning of f of A, of my interval here, has to be equal to the same value as the last part of my point. All right? When those 3 criteria are met, then there is at least one point where my derivative is 0. Well, let's get a big fat no duh, right? So think about what was just said here. I have some interval here from A to B. I don't know what it is. I don't know. I've got some point B, some point A. And I've got an interval that goes between those two. Now, with this interval that goes between those two, I don't know what my graph is doing. I don't know. It could be anything, right? But here's the point. What does it mean when you have a derivative equal to 0? Yes, that's that max or min, right? That's that horizontal tangent. If I start here and I end here, then I'm going to have, at some point, whatever is happening between here, I've got all of these horizontal tangents that are happening. What does this say? At least one point is going to have that horizontal tangent. Well, I could have something like this. Do I have at least one horizontal tangent? Yes, right? What if we have something, I don't know, it's not quite as crazy and I'm just doing something like this? Do I have at least one horizontal tangent? Yes. Okay, so that's the whole point here then, right? I could have a whole ton of them, or I could have at least one. That's the point that we're making. That is Rolle's theorem. If these 3 criteria are met, it has to be continuous. I can't have any breaks in here. I can't have any asymptotes. I can't have any piecewise. I can't have anything. As long as it's continuous, I know from A to B, whatever my graph is doing, I don't care. It has to be continuous and it has to be differentiable, right? So I can't have any cusps that go through there because then it's not differentiable. And that's also when I don't have a derivative equal to 0. Right. And the first value has to be equal to the last value so that I know that it's on the same playing field. So somehow I have to start here, something happens, and I have to end here. So whatever happens, I know I have to go up and then back to it, down and then back to it, whatever. But I will have that derivative equal to 0 for that critical value. Okay, let's do one. The ones in your book are not super awesome in my opinion, like the examples. So we're going to just do some examples out of the exercises. So we're going to start here with 4.2.11. And we're going to use Rolle's theorem. F of x is equal to x times x minus 1 squared on the interval from 0 to 1. So anytime it says use Rolle's theorem, immediately, these are proofs, immediately go through those three criteria. Criteria number 1, continuous. And you have to know these because you know I'm not giving them to you. Rolle's theorem, you have to know these three criteria. Number 1, is it continuous? Number 2, is it differentiable? And number 3, does that first term value equal that last term value? Or that last part of my interval? Oh, let's figure this out. Step 1, is this continuous? Here's my function. Is that function continuous? Yes! What is that? That's just a polynomial, right? Yes, a polynomial. Whoa, that doesn't look anything like the word yes. Well, maybe a little bit, but not very good. Yes, because it's a polynomial. Now, here's the deal whenever it comes to this. Just because I don't want you giving me some Pavlovian response, yes, yes, without having any clue of why you're saying it, you have to give me a reason. You have to give me a reason, not because Rolle's theorem dictates it, but because I do. That's why. I need to know you're not just saying yes to get through the problem. You need to know why that is continuous. That's the concept of a proof. I need you to know why this is differentiable. Why is it? Yeah, again, it's a polynomial. Anytime you have a polynomial, it's your best day ever. So you know polynomials are always continuous and always differentiable everywhere. Love them. Now, if I'm looking at this, I have to say f of 0 because this is my a to my b, right? So f of 0 is equal to 0 times 0 minus 1 squared. So f of 0 is 0. Nailed it. Now let's try f of 1, right? Because that's my b. 1 times 1 minus 1. Well, what's 1 minus 1? A 0. So f of 1 also equals 0. Is my last criteria met? Yes. All right. 3 criteria are met. Let me squeeze this back down. As soon as those 3 criteria are met, then I set my derivative equal to 0. And that's what we're going to do now. So in order to set a derivative equal to 0, we got to take a derivative. F prime of x. You can go ahead and multiply all this out, but frankly, as kind of wimpy as this one is, I'm just going to do the product rule. I think that's going to be easier. So when you take the derivative of the first, that's just a 1, right, times the second, plus the first times the derivative of the second, right? Because the derivative here is bring the 2 in front. So, well, it looks like I was put to that x. The 2 in front, because it's the second part. So I've got 2 times keeping the guts times the derivative of the inside, and that's just 1. So it's really not too bad. Yeah. Okay. So now look at what's happening. Be smart about this. We know we're going to have to set this equal to 0. We're going to have to set this equal to 0 because that's what my criteria says. So if you can factor up front, do it. Look at what this is. There is an x minus 1 in common. Don't go multiplying that out. You're just going to have to factor it out later. If you can see where that's already set up, factor it out now. Okay, I know I'm making you sick back and forth with this. Sorry. Hang in with me. All right, so f prime of x is equal to, if I factor out this x minus 1, I'm left with an x minus 1 plus a 2x. And then just combine those like terms. So my derivative is equal to x minus 1 times a 3x minus 1. And that's my derivative. And I'm told to set my derivative equal to 0. So when you set your derivative equal to 0, and it's already factored, that's my best day ever. I know x is equal to 1 and x is equal to a 1/3. Now, when I'm looking at these points, let me squeeze this back in here. What did this up here, this criteria say? It is continuous on the closed interval, but it's differentiable on the what? Open interval. It has to be differentiable on the open interval. And there's at least a point C that is what? In the open interval, so that my derivative is equal to this. I'm not about to put this value 1 here because that's on the outside of my interval. I am looking at all of the values inside that interval because it's on the open, right? That's what parentheses means. Open intervals, everything between, just not counting the two outside values. So let me squeeze this in so you can see it better. Make this bigger. This 1 right here, I'm going to snake it up there. Hitting on that 1, that's not going to work because I have to have an open interval. Do you see that? So what's the only value that is going to work there? Yeah, 1/3. So whenever I say at least 1, in this instance, I just have that 1 at 1/3 because I only want this specific interval. I'm only wanting this interval. We know it's a polynomial and it's continuous forever, but I want to focus what I'm looking for. If I just focus what I'm looking for, I'm just focusing in here on this 0 to 1, right? So I'm saying from this interval here, from 0 here to 1, and we know it's a polynomial that we have that's a positive. Here, I can go however I go, but I know at 1/3, I'm going to have that horizontal tangent. All right. Okay. So this says use Rolle's theorem. So I know that my x value here is going to be 1/3. It says find a point on that. I don't know if they're going to actually have you find a point or not, but let's go ahead and do it here for this one just to make sure that we're on the up and up with it. Usually they just want you to find the x value where that's going to happen, but just in case. So if it asks me to find the actual point, then we just plug that 1/3 into the original. So it's 1/3 times 1/3 minus 1 squared. It's not so bad. 1/3 times a negative 2/3 squared. So 1/3 times 4/9. So that's 4/27. So my coordinate point is 1/3, 4/27. It's not that bad to find those. Right? Okay. So if you want to find the actual point, you plug it back into the original, because just like when we were graphing, the original is where you get your points from it. All right. Good job.